Hello, this is the lightning talk for the Autonomous Delivery Robot MSD project, and these are our team members.
Start off, mechanical for our group is supporting upgrades and implementing sensors and payloads via a universal sensor mount. This sensor mount is easily changeable and simple in design for ease of manufacturing and integration with new sensors if needed in the future. Currently, the robot has a LiDAR at the top of the sensor mount for autonomous navigation. The payload compartment, the blue box in the back of the robot, of the sensor mount allows for the autonomous robot to deliver materials around the lab as needed. In addition to this, the mechanical team supported upgrades and electrical mounting and modifications that you'll hear about next.
The electrical team upgraded the robot's battery system, allowing it to be charged without disassembling the robot. This was accomplished using a TI evaluation module with an I2C interface that allowed the main processor to monitor the charging current of the batteries. The 10 amp charge rate strikes a balance between fast charge time and battery safety. On the next slide, you'll also see the electrical team's contribution to researching inductive coils that would allow the robot to be charged wirelessly. The coils we tested were determined not to provide sufficient power, so this idea was benched in favor of plug-in charging. However, we laid the groundwork of research to enable future teams to build a wireless charging system provided they find sufficient coils.
Now on the software side of things, first the software team utilized the internal motor encoders and tuned odometry data so the robot could understand its positional drift moving forward or backward. Next, they utilized the IMU, which was configured for use in localization to understand positional metrics of the robot.
LiDAR data was used to collect locational and obstacle data that would be presented in front of the robot, and SLAM was used for localization of the robot's current position and aid in path planning for where the robot goes to next.
The nav2 package was utilized to create the local cost maps as well as the paths that the robot would follow as it moved forward. And finally, the gazebo simulation environment was used to simulate the robot in a semi-real world environment as seen in the next couple slides.